Welcome to ECE, what class am I in? 320A. Better make sure which class I'm supposed to be lecturing to. Can everyone see the screen? That's how I will be presenting the material is on the screen, hopefully. If you can see that, we're in pretty good shape. I don't think I'm going to be using the whiteboard unless I have a problem with technology, which we've already experienced, correct? But we'll try to get started. I'm going to hand around, before maybe we do that, I'm Hal Tharp. I will be your instructor for ECE 320A. I'm going to be passing around three different sheets, but two different types of sheets. One is attachment 1, which if you want to add the class, then go ahead and sign your name to attachment 1. If you are if you are already in the class, then you're looking for attachment 2, and you sign attachment 2. Is that clear? There's 2 attachment 2 sheets that will be passed around, and only one attachment 1 sheet. Just make sure you sign only one sheet as it's going around. Hopefully most of you will be signing attachment number 2 is the idea. We'll try to most classes with the following, the announcements. I'll just post those up, and then some goals that we're trying to accomplish during the particular lecture. There's the sign-up sheet, and then you have a passport assignment that's due on Saturday. And hopefully you do have D2L access, and that's your access into the machine or into the class. Handing in that passport assignment, and that should be on D2L. On the content page, you will find the assignment. You can submit that through the Dropbox on D2L, and if you have questions, let me know, but hopefully that will go smoothly. What I want to do is the following. Just go through some basic bookkeeping. One is these lectures are being recorded, and that means potentially they will be available to you on the D2L website. You can click and you can actually hear what's going on and also see what I was scribbling on the screen simultaneously with my audio. Yes, sir. They are still being recorded. I'm just not plugged into the classroom mic. So hopefully they are still being recorded into my system if I plugged the correct jack into the right thing and somebody was thirsty and it's hot out and there's water all over. So who knows what's going to happen electrically up here on the counter, but hopefully we'll be okay. Yes, the plan is to have them recorded. If they don't get recorded, then we'll figure out what to do next. Maybe I'll just sit in my office and redo the lecture. I don't know if it's that important to you. You'll still have the notes, hopefully. Attendance, that should be being passed around. Sign one of those attachments. Let's now talk about this passport that I was saying is your ticket into the class. That's so that I can try to identify you out of this class of 70 students. Hopefully you made it across the mall. That was pretty busy or intense. I had to fight my way across the mall. Hopefully not too many people were hurt. Provide your name, your real name, and then if you go by something else, that's what's there. That's what the nickname is for. So if your real name is John and you actually go by Pete, go ahead and say Pete for your nickname. And then the email, an up-to-date photograph, not your baby picture. I probably won't be able to extrapolate the age separation between infancy and 20. I'm not very good, especially there's a lot of change in those 20 years, right? Hopefully in the next 20 there's not as many changes, and you would like to think that in the last 20 there wouldn't be many, but unfortunately there are. Okay. Interesting fact about you, something that I will be able to remember you by, and that won't be recorded. visuals. Unfortunately, you won't see those in the recording, or maybe luckily you will. Then there's a learning styles quiz that I want you to take online and report your results. Don't just copy these down. You'll learn that you might be on some particular location in these paired up learning styles, active or reflective. Maybe you're more reflective than you are active, and it will give you a number that you are maybe a 3 on the reflective scale, or maybe you're an 11. Just write those down with reflective or sensing, whatever you end up being. And then there's a question on a current event, just to see if you're engaged with the material that we will be covering in 320A and what's going on around you. That's the point of this particular question. And then I ask if you've looked at and understand the syllabus, which is the next item that we will talk about. This is 320A if you're just coming in from the mall. My office hours will be held in room 523. That's on the 5th floor of the ECE building. Those office hours, I just had one. I missed you. But I have office hours on Tuesdays and Thursdays before class from 11 until noon, and Wednesday afternoon from 2 until right before my next class on Wednesday afternoon. And so I'll say 3:45 is when we'll stop that. But I think those blocks are supposed to be consistent if you are a first semester junior. These shouldn't overlap too much with your other classes that you might be scheduled to take and your labs. If you're not in ECE, then it may be a little bit more of a challenge, but let me know and we can set up some other office hours if those would be needed or helpful. The first page gives you some information about the course, why you might want to be taking it. Well, it's required if you're in ECE. That's maybe the main point. Some tips for succeeding and my teaching philosophy. The textbook, hopefully you already have access to that. That should be very familiar. Hopefully no one's really breaking out in a cold sweat after you see that cover. But that's the book that you've already used in 220. We will now be covering the second half of that textbook, and that means we're starting in chapter 10 and working our way down to the end, which is chapter 18. That's the idea. And that should be available to you in the front part of your book. This is just a scan, a pour scan of the quick table of contents for your textbook. Maybe what you're more concerned with are the grading breakdowns. And what we're doing this semester, hopefully, will be 3 in-class exams. Those will be then the 75 minutes. Those are tentative dates, but we'll try to stick with those. Homework will be worth 10% of your grade, and the final exam will be 30% of your grade. And this syllabus, the passport, those are all available on the D2L website. So you can download those if you want, or you can look at it more carefully at that point. With a Tuesday, Thursday class this semester, the only day that we get off is during the Thanksgiving recess. Obviously, you'll get off days after December 17th, but that's after the semester is complete. And the final is a little different in terms of time. Isn't it about 12:30 now? So you'll have to set your alarm earlier if you're just now waking up for the final when it occurs on the 17th of December. The final exam ends at 12:30. You don't want to show up at 12:30 on December 17th. Okay, make sure you show up at 10:30. And that is a Tuesday, but you need to pay attention to your other classes. Sometimes you'll have a Monday, Wednesday, Friday class, and its final will be on a Tuesday and Thursday. So be really careful with your final exams when they are scheduled to occur. Then by the end of the course, you should be able to do these 10 things, or even more than that. I just tried to collapse those down into some very broad descriptions. And this last page of the syllabus simply goes through the different sections in the textbook, but that's essentially how we will linearly follow through the presentation of the material. When we get to the end, we might be jumping around a little bit. Maybe we will cover 2-port networks before we get into Fourier series, which are 16 and 17, but at that point, it doesn't matter that we're jumping around. You've already had sufficient information to be able to perform up to what you need by chapter 18 once we've covered, let's say, chapter 14. Questions on the syllabus or the class in general? And if you do provide me with a question, I will try to repeat it so that it does get recorded. That's somewhat frustrating when you're hearing an answer and you don't know the question. So if I didn't repeat the question, you can point that out to me and say, what was the question again? I'm not going to be upset at you for doing that. I get upset real easy. We'll see. All right, we've done that. Now it's time for you. Here's a quiz. I want you to now find the output voltage, which is on the right of this circuit. You have a sinusoidal input exciting your system, and you can assume that that's been on forever, and now you want to find the sinusoidal steady state output. This should be a review of what you finished in ECE 220. That's the idea. You have some, and those squiggly things are inductors, the sharper things are resistors. The appropriate values, that's a 78, not 7B for the resistor value. Hopefully you'll start to learn my notation. Is it clear what you're supposed to be doing? By the silence, I'll take that as a yes. You don't have a calculator. Well, you can plug in some of the numbers or at least set it up, right? What if you don't know where to start? And I'm sure that's not the case for any of you. What if you were given this on a job interview, this question? Is that the cold sweat that we'd talked about before? Would you break out into a cold sweat? Well, what you might try to do is actually put something down. And how do you put something down? Well, you might say, you know what? Let me just kind of warm up. I need to kind of get loosened up. How about I just neglect some things? Let me simplify the problem. That might be a way to get you thinking and getting back off of this summer break that you're experiencing. So let's just now say, how could we now simplify the problem if we didn't really know where we were going to start? So now you're trying to get your feet wet, and I'm getting everything else wet up here on the table, but you can get your feet wet. How would you simplify this? How would you like to have this problem be stated to you? In terms of impedances, let's simplify it even more than that. Well, no sinusoids. So you could just say, oh, let's do a DC analysis. Let's assume that we have a sinusoidal input, but what if we simply shorted out the inductors? Just replace those inductors with wires. Then we would have a pure resistive circuit, right? So if we neglect the inductors, this is not to say that this is the answer, but at least we're getting something on the paper for this potential boss that we might be dealing with. Meaning we can now say, well, let me just sort of think out loud for this potential employer. And you say, there's my voltage source. I'm used to seeing them in something. Maybe now I have a circle. And suppose that, just for starters, why don't I neglect the inductors? And I was saying that this was maybe the line impedance. That's a transmission line. That's what we're going to be starting with when we start to do this class. Then we had a load resistor. So one of those L's is lowercase, one is uppercase, and that's important to distinguish the line and the load. And it was 78 ohms. And now we have not V sub L, but we have an approximation to that. And now can you solve the problem? Now is it easier? Now do you have a feel for what's going on? What's happening in this circuit? It's a voltage divider, isn't it? You now have, and is it really getting divided down much? What's your total total resistance? 80. And what fraction are you seeing at the output? 78. So you're not dividing this down much at all at DC. You're pretty much seeing at the output, V sub L, what you're putting in at the input, V sub S. These are the kinds of questions you need to start asking yourself when you're looking at circuits, just so that you can start to get a better feel for what's going on and how to analyze it. In this case, then, you said, okay, let's solve this via the voltage divider. Or if you wanted to, maybe you don't like the voltage divider, you could have found the current in that loop or in that single mesh. That wouldn't have been too hard. And maybe we would want to indicate where our current was. But whatever we're doing, so if we did that, if we found the current, then we would say, oh, V sub L hat is now this load resistance times I of t, but I of t in this case was simply V sub S of t over the total resistance, which was the sum of those two resistors. And that's now a very quick solution, and you didn't need a calculator, did you? And you could, not for this part, and you could sort of think your way through it. And now you know that if your input oh, that's a great sine wave. You'll do better than I can. But that's, let's say this is now V sub S of t. And now what's going to happen with V sub L hat of t? What's it going to look like? Pardon? The peaks will be a little bit lower. Well, where will the peaks be relative to the peaks on V sub S of t? In time. Where will they be relative to each other? They'll be at the same time, won't they? Because this is a purely resistive circuit. There's no memory. There's no energy storage with those inductors gone, with those inductors shorted. Meaning our peaks and valleys need to be lined up. And I'm going to over-exaggerate this, but it's not much less, actually, is it? It's this 78 to 80 ratio. That fraction is going to impact the difference between the output voltage and the input voltage in this simplified circuit when we simply have pure resistors in play. Now, if we say, okay, that maybe got me started, now maybe he's feeling a little bit more comfortable that I did take something in electrical and computer engineering, or she, whoever is doing the interviewing. What are some of the important pieces now if we go back to the original diagram or circuit? If we say what's important about the input voltage, what would you say? Okay, we need to know the actual value of the amplitude. In this case, it's 311.1. And drawn this way as a time domain expression, that's the maximum. That's the peak amplitude of that sinusoid, which in this case is a cosine waveform. The other important piece is the frequency. Somebody was saying, why don't we get the impedances? Or it would be helpful if I had the impedances. Well, the impedances are very dependent on the frequency. And the frequency, omega in angular frequency, radians per second, is 2 pi 60, 120 pi. And pi, maybe we'll have to avoid pi in this class since this class is right after noon, and I'm thinking of the round fruit version of pi, not the 3.14159. Anyway, sorry. That was a little aside, but I'm hungry. So if we go back a little bit to the original circuit, then one piece that's important is this omega, which is 2 pi f. And 60 is what's coming out of the jacks here in the United States. If you go somewhere else, maybe in Europe, maybe it's 50 hertz. But here it's 60 hertz. We know F. That was given. That was isolated out as the 60 in that expression. And in this class, we'll be doing a lot of things with 60 hertz. And so knowing 2 pi times 60 is roughly 377. Now you can memorize that and you won't need your calculator. Maybe we'll just do away with calculators on the exam. How's that? You guys get very dependent on those calculators. They're almost like a security device, aren't they? Like your pacifier or your blanket when we're going back to your baby picture. At that time frame, well, I won't say anymore. Now with this, omega, now we can say, you know what? He said that source was happening for all time. So we're in a sinusoidal steady state. We don't have to worry about any transients. And if we're working with sinusoidal steady state, that now starts to look like that DC problem if we start playing not with just real numbers, but if we start working with phasors or complex quantities. For example, now we can find these impedances. What's the expression for the impedance of an inductor? Do you remember that from 220? Well, there's a lot of bells in here, aren't they? So in electrical engineering, we reserve I for current, don't we? So we like to use J omega L, and I'll say L sub L since that was our load inductor. We now have J times 377, and I'm going from my notes. I don't want to scroll back. I think that impedance value was 156.5 millihenries. Now maybe you need your calculator. Maybe we'll switch to slide rules. Does everyone have a slide rule you can bring in for your, we're going before your baby picture, aren't we, with slide rules? If you do that calculation, hopefully you'll get something close to 59. Now that impedance of that inductor is J59. And we can do an equivalent, or I should say a similar computation for the line inductor. Our frequency hasn't changed. The only thing that's changed is our inductor value, which in this case was 2.653 or 2.6 millihenries, roughly. And that ends up being 1 in value. If we're now playing with phasors and impedances, what's the impedance of that line resistor? What's its formula? If you're given a resistor and you're asked for its impedance, pardon? It's trivial, right? Why are you asking? Well, I need you to explain that you know that, right? This is just the resistor value. It's not a function of frequency. That was how we were able to solve our original problem. We didn't have to worry about frequency. And likewise, the impedance of the load resistor is just capital R sub capital L, which was 78. Now we have the elements in our circuit modeled by complex impedance values. If we convert our source was V sub S of t was equal to 311.1 cosine of 377t. If we put that into phasor form, how would we write that? We can just copy down the magnitude, and we could say, okay, we'll just keep on the side of our paper the fact that we're dealing with cosines, and we'll just use the angle relative to the cosine waveform. In this case, that cosine waveform has an angle of 0. And here, this magnitude or value is actually Vmax, or the peak value or maximum value of that source. Now, we may want to convert that to RMS values when we're doing our power computations in this class. Meaning we could write another phasor if we wanted to. We could say, well, let me write that as V sub S RMS. That's now just going to be V sub S max over the square root of 2, and the angle hasn't changed. And if we do that computation, we end up with 220 volts RMS, and that sounds like something we might actually have in our house, powering our air conditioner or our dryer. It's not coming out of most of these generic outlets, but we do have the potential of a 220. Now we can redraw our circuit, can't we? Now we can look at this circuit in the phasor domain. Oh, let me just go ahead and put it in at the numerical values. Let me say it's 220. At 0 degrees. Here's the 2, here's the J1. This was 78, and this was J59. And now we could solve this in our favorite way. Let's say that we wanted to find this phasor current that's flowing through that circuit. Now we know that we could simply add up all of our well, let's go ahead and kind of play through this. I don't even have my calculated value, so now I'm getting nervous, right? But we know that V sub L is going to be what? If we knew I sub t, what is the phasor V sub L bar? Is everybody okay or comfortable with that? And I sub t, if we needed it, would be this 220 at 0 degrees. And what was this? Was this 2 plus J1 plus 78 plus J59? Or this now becomes 80 plus J60. And that's our 3, 4, 5 triangle, isn't it? Sort of, scaled by 2. And then we could find its amplitude. That amplitude is 100, isn't it? At a given angle. And we could draw the picture to find out where are we relative to 60 and 80 in terms of this picture. Meaning we now know that the total impedance you could think of in terms of, let's just say this is values of 20. We're going 80 to the right and 60 up. That's now our picture in polar form of our impedance. So if we wanted to, this would be now the magnitude of that impedance, Z sub t. And that should be what value? Square root of 60 squared plus 80 squared, which is 100, right? And that angle is the inverse tangent of 60 over 80. So we now know what Z sub t was. Z sub t is now this square root of real part squared plus imaginary part squared at an angle that has an inverse tangent of 60 over 80, or the inverse tangent of 3 over 4. And you can sort of visually see what that angle is. It's less than 45, isn't it? So now if your calculator gives you 60 degrees, you go, uh-oh, either I'm not thinking through this problem correctly, or I entered some numbers wrong on my calculator. And that's why you want to start maybe quickly drawing some of these numbers or pictures out to keep yourself in line or a little bit more accurate. Questions on that? Now you know how to solve that problem, correct? Well, we haven't done it completely, but you could find V, what did we call it? V sub L bar. That would be its phasor form. You should be able to immediately pull that back into the time domain. And it's going to be a cosine waveform. And now, how will the peaks of that sinusoid at the output, how will those peaks be associated with the peaks in the original voltage source? They'll be shifted in time, won't they? Because now we have a phase shift between the output and the input. And the amplitude might be a little different than what our original idealized pure resistive circuit looked like. What we're going to be playing with, beginning with, is power in this class. And if I said, what's the instantaneous power, what would just the generic formula be for instantaneous power? VI, right? So that's now V of t times I of t. What we'll find is that might be a little bit messy. Now V is a sinusoid, I is a sinusoid, multiplying that out. Now we're back in trigonometry, trying to figure out what are products of sines and cosines, or cosines and cosines, etc. We like to work things a little more easily. And for that reason, maybe we don't want to know what's happening instantaneously with the power. If this has happened for a long time, maybe we're just happy with the average power. And that's what we're going to be starting to worry about, are these different kinds of power in this class. One of those will be the average power, or the real power. And it will have, and we'll keep these different powers separated by the units that we assign to those. And this is what you will see from the power company. You'll get a bill and it will show how many, well, it may actually show you the energy consumed. It'll be watt hours or kilowatt hours. But there's a watt in there, isn't there? It's just multiplied by a time to give you the energy. But you could then divide out that time and get the total or your average power that you had over a 1 month period, for example. Now, we are going to be playing with circuits that are more than just resistors. If we just had resistor circuits, then we would only have to worry about average power, because then the voltage and the current and all the voltages would all be synced up. The peaks would all be aligned and the minimums or the valleys would all be aligned. We're going to make our life a little bit more interesting, and it's going to be more like reality, because if we now have a motor or a bunch of machines in our factory, they are going to present themselves looking more like inductors in terms of they have inductive pieces to them or inductive parts to those. So we need to include some of this inductance in our analysis, and that's going to throw our peaks and valleys off. And it's going to give us more than just average power. Now we're going to have power that's really not even consumed. It's getting thrown back and forth between me and the power company, or you and the power company. We'll learn more about these concepts as we go, but that's reactive power. And that has different units. In general, power was volts times current. Well, volts has units of volts, and current has units of amps. So we will call this volt amperes reactive, or VARs. So our reactive power will have units of VARs. And if I say, what's the reactive power in that load? You'll be able to find it, and you'll label it and say, oh, that's VARs. Or maybe it's kilovars. Now, we are going to want to keep track of both of those. Well, the power company wants to know that, because the presence of reactive power actually means that they have to produce maybe a higher voltage and supply more current to give you the real power that you need at your end of the line. So they're now having to generate more to make you happy. And the more inductive loads you have, the more variation there is, or the more reactive power you might have. Well, the power company is going to not let you get away with that. They're going to charge you for what you're using, or what they're having to supply to you. And for that reason, we want to keep track of both of these. And the way that we do that is we combine those. The average power, if you're thinking sort of visually, we will keep the average power on the real axis. And we'll go orthogonal to that for the reactive power. And we'll combine those into one complex quantity, and that's the complex power. And this has units of volt amperes. Now, if we have a complex number, you can write that in many different ways. And in this class, mainly two ways. We have rectangular form and polar form. In the polar form, we get a magnitude, and that magnitude, if we find the magnitude of our complex power, that's the apparent power, and that's what the power company keeps track of. They go, this is how much apparently we're having to give you so that you can operate your machines in your plant. So they want to know sort of what's the difference between the apparent power and the average power, or real power, and that's this power factor, and we'll learn more about that also. But this apparent power, the reactive power, and this complex power, those may all be new to you. Have you heard of those before? You probably don't have those on your power bill unless you're working for a company. And then they keep very close tabs of that. Because if you have a lot of machines in your plant, you may want to say, you know what, let's try to make our power factor closer to 1 or make it look more like just a resistive plant. Well, if we have a bunch of inductors, how do you maybe make that look more like a resistor? How do you sort of complement inductors? Or what's sort of the opposite capacitors? So now you may have a capacitor bank and you may be switching that in and out of your circuit so that your plant looks more like just a resistor to the power company. And if it doesn't, there's a surcharge and you're going to be charged more for the power that you're actually using if you present a big inductive load. Now, that is all there in just we just had one cosine, didn't we, in that source. We'll generalize that. If you go out and start looking around, now when you go home, you might start looking around and seeing, where are the power lines? Because I'm learning about that now in 320A. Well, you may see more than just one line. You may see 3 lines, maybe 4. But we now need to worry about different phases. What we've just been talking about was a single phase circuit. We need to, in this class, start studying 3-phase systems. We'll have an A phase, a B phase, and a C phase. We'll also talk about a positive phase sequence and a negative phase sequence. And that depends on whether A is ahead of B is ahead of C, or if A is ahead of C is ahead of B. This will all make sense as we go. But we'll start talking about different phase sequences, whether it's a positive phase sequence or a negative phase sequence, and that's important for analyzing these 3-phase systems. If everything is balanced, we'll be able to distill that 3-phase system down to just a single-phase system. And we can do our analysis on the single phase and then back out all the other numbers or the quantities that we want. That's the very first part of this semester. That's maybe exam number 1, that material, playing with that. And obviously we have quite a bit to learn in just the definitions. And where do those come from and how can we use those? What we will then do is we will generalize That was pretty nice, wasn't it? The way that we were able to use phasor notation to simplify that circuit, and instead of working in the time domain. If we were working in the time domain, we would have had a bunch of differential equations with all those inductors, because their current voltage relationship is not V is equal to Ri, is it? And we'll talk about Eli and ice. Maybe not today, maybe we will. But that's a way to keep track of inductor current voltage relationships and capacitor current voltage relationships. What's the expression for an inductor's voltage in terms of the current? Do you remember? Not in impedance terms or not in phasor terms, but in differential terms or in the time domain. V sub L of t is equal to L di dt. And the capacitor is I sub C of t is equal to C dV sub C dt. Knowing that moves you quite long or quite far down the road. But again, maybe we don't want to play with time domain expressions all the time. And what we will then do is we will generalize these sinusoidal steady state or phasor analysis techniques into the S domain, where we are now going to be using Laplace transforms. The nice thing about Laplace transforms is now we can start playing with transients. We don't have to just worry about always being in a sinusoidal steady state. The Laplace transform will allow us to analyze our circuit with ups and downs or transients occurring. And we can still play with steady state analysis if we were, let's say, forcing our system with a bunch of sine waves, or because it allows for transients, we can now incorporate initial conditions. The other thing that this buys us is that we can fairly easily generalize all of our analysis techniques. You should be able to do Ohm's law, and you now know the current voltage relationships of the inductors and capacitors. You should be able to do KCL and KVL. You should be able to do mesh analysis, nodal analysis, and what we can now do is more easily play with circuits that are more than just first order or second order. And I think that's what you were playing with in 220. First order transients and second order. Underdamped, overdamped, critically damped. We can now play with more than just one or two energy storage elements. And by energy storage elements in this class, what that means is inductors and capacitors. We could have a complicated circuit, and now we can play with it. We can now not just look at the impedance, we can generalize that impedance to have our impedances represented in terms of S, or this complex variable S. That will allow us to come up with transfer functions, meaning we might have a relationship between some voltage and the circuit and maybe some input. So maybe this is our output voltage V sub O. We have an input voltage V sub I, and this transfer function represents our system. And now, pictorially, we can think of replacing this complicated circuit with just a block diagram that's maybe easier to think about. And once we have that H of S, we know a lot about our system. We can now do a lot of different things. We could, if we wanted to, we could go back into the time domain and we could find that's supposed to be a script L inverted. That's the inverse Laplace transform of our transfer function. And this now is the impulse response of a circuit. Or we could take H of S and evaluate that, or replace this S. S is a complex number, and we'll think of that as this complex S plane with a real part and an imaginary part. And the imaginary part we could think of as living on the imaginary axis, and that's when S is equal to j omega. If we let S equal to j omega in our transfer function, now we have this frequency response behavior of our system. This will tell us how our system behaves at all these different frequencies. And you might say, what's he talking about? What is h of j omega? J is our complex number, right? We can now sketch this and get a picture. We're very visual. We like pictures, and maybe instead of equations. What's a picture for our system? What's its frequency response? This is now going to allow us to figure out what's the frequency response of our system. And a picture of that will be a Bode plot. Actually, it's Bode plots. We'll plot the magnitude versus frequency and the angle versus frequency, or the phase versus frequency. The magnitude plot, you could think of your stereo. How do you like to listen to music? Do you like to emphasize low frequencies? You increase the bass. Maybe you want to hear the vocals. Maybe your mid-range is higher. Maybe you don't like all that tweeter stuff, so you reduce the high frequencies. Well, that's now giving you a frequency response shape. That's what we will do with our systems. We'll figure out what does it look like in the frequency domain. What is the frequency response? And that will allow us to very quickly do sinusoidal steady state analysis if we wanted to. Another possibility is if we have h of t and somebody now excites our system with, let's say, v sub I of t, and you want to do that in the time domain, now we can start talking about convolution. Where this is now some a generic input voltage. This is the impulse response of our system. And convolution will allow us to find v sub 0 of t, which we will denote as h of t convolved with v sub I of t. That's more than just a multiplication symbol. This is now this convolution. Have you had convolution before? No's, yeses. Maybe most of you are shaking your head from left to right. We'll learn how to convolve two waveforms and what that means. But that's now a time domain way of thinking about the response of your system. This would now be the output response. V sub I of t is some generic input. Maybe somebody says, you know what? I now have an input. Let's say that I apply this. Maybe this is now V sub I of t. Here's our time. And now they say, well, what happens if you low pass filter that? What's going to be the output if you low pass filter that pulse? Any ideas? These sharp edges, those are very high frequency in content. And if we low pass filter, we're going to round those edges. And depending on how hard we hit it with a low pass filter, this now may look more like do you recognize that response? Maybe a first order transient. And then after you turn off the input, so this might be your V sub O of t, and maybe your impulse response looked something like that. And we'll learn how to find all of these expressions and then how to convolve this blue line with the other blue line to generate that red line. And that's via convolution. We could also solve it in the Laplace domain, an inverse Laplace transform, to find little v sub 0 of t. What are we doing? Well, I just said, what if we low-pass filter? We're going to learn how to build those up in this class. We're going to be talking about filters. And we'll start that process with the basics, or with passive filters. Meaning, maybe what you that's a classic low-pass filter, passive low-pass filter. How big is it? It's not very big. It's first order. It only has one energy storage device. We can analyze that to death if we want to, but you should be able to understand that or play with that a lot. But this is now a passive low-pass filter. And the choice, if you now go over to Josie in the stockroom and say, I need to build a low-pass filter. Okay. What are you going to do? You're going to have to request a resistor and a capacitor if you did a first-order low-pass filter. You now need to figure out, what's my bandwidth? What frequencies do I want to pass? Which frequencies do I want to throw away or get rid of or attenuate? That's going to influence your choice of R and C. And we'll learn how to pick those values to give us the cutoff frequency or the bandwidth that we're interested in. That's now a passive low-pass filter. And you could play with a lot of different R's, L's, and C's. It's passive because we don't have to power those circuit elements to make them work. They just work on their own. They don't need any external supplies to function. So it's passive. That's where the passive comes from. We will also start playing with active filters. And when we're playing with active filters, now we're dealing with op amps. That's what we'll play with here. Now we have these ideal circuit elements that are op amps. And an op amp, a lot of times it's not indicated in your diagram, but you have to physically power those, don't you? They have a plus and minus terminal, and you have to energize those to make them work. But once you've got them working, now we can put those together in a nice configuration and maybe make a more interesting filter. And we'll start talking about, man, Butterworth. Now I'm thinking about pancakes. Butterworth filters. Those are maximally flat. So if you hear Butterworth, this is how I remember, and that pass band is really flat. What's a pancake? Flat as a pancake, right? So that Butterworth filter response has a maximally flat pass band, and you can sort of say, what was Tharp saying about Butterworth? And all I remember is syrup. Well, remember what you put syrup on, which is a pancake, and what do you always say about a pancake? It's flat. It's flatter than Kansas. They've done the study. No, I'm sorry. Kansas is flatter than a pancake. That's the correct study. Got my converse statements in the wrong location. Kansas is flatter than a pancake. Pretty flat, huh? You need to stay awake when you're driving across Kansas. where were we? Oh, active filters and Butterworth. So now we might be thinking, and what are we talking about? Now we're talking about frequency response. Now we could be thinking, I want a filter that looks like that. And this might be the magnitude response, and we'll talk about something being in dB, decibels. In this picture, that's maybe our cutoff frequency, or where we start to change from passing frequencies. That's our pass band, and our cutoff frequencies, or the stop band frequencies, or those frequencies that we're trying to get rid of. And we'll try to build these up, and maybe we want to really make that transition from the pass band into the stop band really, really sharp. That means we need more op amps. That means we need a higher order filter. The higher order we have, the sharper that slope is going to be. And we're going to learn about that and figure out what we need. We'll learn how to find or design this omega sub b. We can then generalize these filters into more generic circuits, which are two-port networks. Now we're looking at saying, you know what? There's a bunch going on in here, but if you just tell me what happens at these two ports, the input port and the output port, if you could parameterize what's going on here, maybe this is 200 transistors and some capacitors and probably not inductors and some resistors. Well, can you boil that down to maybe 4 values to give me 2-port parameters? Then I can analyze more effectively what's going to happen between the input and the output. And those are our 2 ports. Now we have a 2-port problem. And you might see that in many different disciplines. The one with all of these transistors might be in electronics. But you might also see S parameters in electromagnetics if you're now looking at transmission of information in different frequency ranges or values. Now you may want to model this particular waveguide or some other system, circuit, that is dealing with electromagnetic waves. Maybe you can now model that with some 2-port parameters. You've now condensed all of this down into these 4 values. And now with those 4 values, you can tell somebody what's going to happen between the input and the output. We start the semester with sinusoids, right? Cosines and sines. We will then generalize that to where now maybe we just worry about general periodic waveforms. So that now maybe instead of exciting our system with and that just goes on and on. It's like the Energizer bunny. That's always happening. There's time, and maybe this is our V sub I of t. Somebody says, you know what? This is the signal that's being applied to your circuit. What's the output? And you go, you're kidding, aren't you? You go, oh, that's a periodic waveform. You're impressing the interviewer, right? Then you say, what's the period of that waveform? You can find that pretty easily, can't you? You can identify the first time where that pattern starts repeating. Once you have the period, that's reciprocally related to the frequency, and now we can find the omega. Once we have the frequency, now we can really start to play. We're going to convert that into what? Fourier series. We'll rewrite that generic general periodic waveform into a bunch of sines and cosines. And now we're back where we started, right? Sines and cosines. Now I'm feeling really comfortable. I can analyze this circuit with sines and cosines. That's why we do Fourier series, to put us back on comfortable footing. That's where we want, hopefully, we will end the class with some Fourier series, meaning now this v sub I of t is going to be some infinite sum. Wow, people are anxious. They heard this class was in here, that's why. Oh, that wasn't funny, huh? A sub n cosine of n omega naught t, let's say plus b sub n sine of n omega naught t, where we may let that n go from, oh, let's just go from 0 to infinity. So that when it's 0, we have our DC piece. We might want to pull that out, and then we have all these other pieces. But omega naught, boy, those people are going to have to quit coming in early, because then that's like a instant switch, huh? You guys start packing up. This is now, omega naught is 2 pi f naught, but we know that f naught and our period t, which we just identified up here, were reciprocally related. There's our capital T. Now we can divide that into 2 pi. Now we know our omega naught, our fundamental frequency. Now that we know our fundamental frequency, we can start finding these coefficients, these capital A sub n's and B sub n's, and now we have all this harmonic content, and somebody gives us a frequency response, they give us a circuit, we can find the frequency response, we can analyze this. That's where we want to end. So I'll let you go. I'll see you on Thursday. Have a good rest of the week, or rest of the midweek, and I'll see you on Thursday.